Hello everyone, am I audible?
Yes, sir, you're audible.
So we'll wait for a few more minutes. Let's let other students join and then we'll start the session. We'll start the session in 2 more minutes. Yeah. Hello everyone. Today we'll be doing solve with this on week 10. So I request everyone to have a pen and paper with you so that I'll be showing you the questions and you'll be solving it. And you can, post the answer in the chat box itself. Join PD is not available right now. So you just post the answer in the chat box. So can we start the session now?
Okay.
Yeah. So before moving to the question, we'll just see a few points about graphs. Okay. So the first point is any vertex in a graph having n vertices can have a maximum possible degree of n minus one. So can someone tell me what this means? The first statement means. Hello, I'm audible, right?
Yes, sir.
Yeah. Just a minute. See, the first statement says suppose a graph has n vertices. Okay. So what is the maximum possible degree of a given vertex? It will be n minus 1, right? So it can be connected to the all remaining nodes, right? So there are n minus 1 nodes possible. So therefore the degree can be maximum n minus 1, correct?
Yes, sir.
Yeah. Now we'll see the second point. The second point says the sum of degrees of all vertices will always be even. So if we take, for example, like just a minute. Yeah. If we take a graph like this one, okay, and we just sum the degree of all the vertices, so that will be an even number. That's what they're saying. So we can see that every edge contribute to 2 degrees, right? So this edge contribute to this 1 degree here and one more degree here, right? So every edge contribute to 2 degrees. Therefore, the if you add the total number of degrees of all the vertices, it will be an even number, right? So everyone got this point?
Yes,
Yes,
sir.
sir.
Yeah. And the third point is, uh, if two vertices can have a degree n minus 1, it means that there will be no vertex with degree 1. So just a minute. Let's say suppose let's take two vertices, these two, and there are again, you know, some other nodes. Let's say there are many nodes. There are n nodes totally. So if this one is connected to all the other remaining nodes, suppose there are n minus 1 nodes, right? So this has degree n minus 1, right? So, and the next, this is the second vertex which has degree again n minus 1. Okay. Suppose if this is true, we can clearly see that there will be no node such that its degree is 1. It will always be 2 or more than 2, right?
Yes, sir.
Because it will be connected to this one and it will be connected to this one also. So therefore, there can't be any vertex with degree 1 if there are two vertex with degree n minus 1. Okay. So everyone got the third point now?
Sir.
Got it.
Yes, sir.
Yeah. So now I think we'll move to the first question. So the first question says we have a graph G with vertices A, B, C, D, and E. Write down the degree of all the vertices in order of A, B, C, and D. Okay. And they are saying the question says which of the following is a possible listing of the degrees. So the options are given. So from the things that we have learned in the previous slide, just try to use that and say which which one of the option can be a possible listing of the degrees. So everyone got this question right? Hello?
Yes, sir.
Yeah. Okay. So after getting the answer, you can just post it in the chat box. You have to post the answer in the chat box. Okay. So everyone who got the answer, just post it in the chat box. Which option is correct? So for students who have joined late, everyone got this question right? Or do you want me to explain it once again? This question. Actually, there is no graph for this question. They're asking which of the following can be a possible listing of degrees. Okay. So, like, do you want me to explain the previous slide once again?
Yes, sir. Actually, I joined it little late, sir. Please.
Okay. Yeah. So just a minute. Is the slide visible now?
Yes.
Yes.
For
Yes,
a
sir.
graph, for a graph, there are like we are just going to see 3 points now. So any vertex in a graph having n vertices can have maximum possible degree of n minus 1. So do you agree with this statement? So everyone agree with this statement?
Yes, sir.
So this is the first statement. Because see, if there are n vertices, it can be connected to n minus 1 other vertices, right? So therefore, the maximum possible degree can be n minus 1. From that also we can say. So the second point says that the sum of the degree of all the vertices will always be even. So like if there are n vertices, if you take the degree of each the vertices and add them, it will always be an even number. That's what this statement says. You are getting it? Hello?
Yeah.
Yes, sir.
Yeah. So everyone got the second point now?
Yes, sir.
Why is it so, sir? Just to
Okay. Just a minute. Suppose see, if there are two vertices and they are connected, this edge is contributing to two nodes, right? I mean degree,
yeah.
this and this one, right? So suppose there are
Okay. Okay.
okay. This will be two now. And this will be one.
Got it. Got it. Okay. Yeah. Yeah. So it will be always multiples of 2. Yeah.
Multiple.
Yeah. Good. Yeah.
And the third point states that if two vertices in a graph have degree n minus 1, it means that there will be no vertex with degree 1. So basically what this says is, suppose let's take this is 1 and this is 2 and there are other nodes here. Okay. So there will be n minus 2 nodes. Okay. So this is connected to all other nodes. Okay. Because it has degree n minus 1, right?
Yes.
So this has degree n minus 1, and this is also even 2 also has degree n minus 1. Okay, so it is also connected to every other. So So from this itself, we can see that there won't be any vertex with degree 1, because any vertex will be connected with 1 also, and any vertex will be connected with 2 also. Therefore, it must have minimum of degree 2, right? So it can't be 1. You're getting my point?
Yeah.
So that's what the third statement is. So now from these things, you try to solve the first question. So they are saying A, B, C, D, E are the vertices. Okay, and they are saying that the vertices, degree of each vertices are written in the order, and they are asking which of the following options can be a possible listing of the degrees. Okay, so which of the following options can be possible? That's what they're asking. So if you got the answer, post it in the chat box. Okay. So I'll give a small hint. Try to use all the 3 points that we discussed previously, and then come up with an answer. Okay.
Also, would you please show the backslash button?
Sorry.
So please show the previous slide.
Previous. Okay, just a minute. Is it okay? So can we discuss the solution, or is anyone still solving the question?
Can discuss.
Okay. So we'll see all the 4 options now.
So there can be more than 2 options, correct?
Like if you are getting more than 2 options, then it can also be correct. Like I don't know.
Okay.
But if you just try using all the 3 things that we have discussed, and then we can see. Okay. So shall I discuss the solution, or still someone solving this question?
Yes,
Can
sir, please discuss.
Sorry.
So discuss.
Okay. So now we'll try to use the first point. Just a minute. Yeah. The first point says any vertex in a graph having n vertices can have a maximum possible degree of n minus 1, right? So how many vertices are there in the graph?
5, sir.
5, right?
5.
So what is the maximum possible degree that this
4.
graph? 4.
4.
So from this, can we say option C is eliminated? So it can
Yes,
be
sir.
Yes. Yes. Yes.
okay. And now we'll try to use the second point. So the sum of the degrees of all vertices will always be even, right? So what we are going to do, we are going to add all those things and check whether they are even or not. Okay. So first tell me what is the sum of option A?
Even
It
12,
is 2, right? Which is even. So we'll sum option B now. So 2 plus 3, 4,
7.
5, 6, 7, right? So this is an odd number. So this option also is not possible, right? Hello?
Right, sir.
Yes, sir.
So option B is also incorrect and option C is also incorrect. Now we'll check option D. It will be 4, 7, 8, 9, 10,
9, 9, 12, sir.
12.
Even.
Yeah, which is an even number. So fourth option can be correct. Now we'll try to check the last statement which is discussed. If two vertices in a graph have degree n minus 1, it means there will be no vertex with degree 1. Okay. So this is what this statement says. So what is the degree? I mean, what is the degree n minus 1 here? N is 5 here, right? So n minus 1 would be 4, right? So first, if you see the first option, there are two, A and B has degree 4, right? Two vertices with degree 4, right?
Yes, sir.
Yes, sir.
Can there be one here?
No, sir.
No, sir.
No, right? So option E is also incorrect. If you can see option D, it satisfies all these conditions, and we can say that the only correct option here is option D. Okay. So everyone got this question? Are there any doubts here?
Sir, I doubt in last point.
Okay. See, this point, the third point states that if two vertices in a graph have degree n minus 1, okay, but what is n here? There are total
5,
n, right? Yeah, 5. So what will be the degree? 4, right?
4. Yes, sir.
If two vertices in a graph have degree 4, it means that there will be no vertex with degree 1. Okay.
Yes, sir, I understand.
There are two vertices with degree 4, but there is also vertices with degree 1, right? D and E have degree 1, which is not possible.
Yes, sir.
Correct. So A option is wrong. Okay. So the correct option will be D.
Yes, sir. Thank
So
you, sir.
one is not possible only when n minus 1 is appearing twice or thrice. It has to be the only once.
Yeah, twice. If it appears twice means, if it appears thrice means what happens? It can't be, 2, right? So because, see, suppose n minus 1, if, graph has 3 n minus,
So would you explain the reason behind that, like to prove that, how it is coming?
see, what I discussed. Suppose let's say this is 1 and this is 2, okay? And let's say there are other vertices. There are totally n minus 2 vertices here, okay? And this is 2. So totally there are n vertices, right? Hello?
Yes, sir.
There are n vertices.
You can also see my board, right? Is my board visible?
Yes,
Yes,
sir.
sir.
Yes, sir. Yes, sir.
See, suppose what the question says, if two vertices have degree n minus 1, which is basically two vertices are connected with every other vertices, okay? So this one is connected with every other vertices and this one is also connected with every other vertices. So then the graph will be like this one. Right? Hello?
Yes, sir.
So this has degree n minus 1. Suppose even 2 also have degree n minus 1. Okay? So the graph will be like this. This can have any degree. We don't care about it now. But what we can say that minimum every node has degree 2, right? Every vertex has degree 2, right?
Yes, sir. Okay, okay, got it. There will not be one then, because two have same.
Suppose that's one more thing. Let's say this is 3, okay, and this is n minus 3 will take, and this is also connected with every other one, okay. So now what will be the minimum degree of each vertex? Each vertex? 3, right?
Three.
Because everything will be connected to 1, 2, and 3. This will be connected to 1, 2, and 3. This will be connected to 1, 2, and 3. This will also be connected to 1, 2, and 3, right? So everything will be connected to 1, 2, and 3 at least. Okay. So therefore, it can't have anything below 3. For example, 2 is not possible. 1 is also not possible. Okay. So everyone got this point?
Yes, sir.
Yeah. Okay. So we'll move to the question again. Just a minute. So we'll just quickly go through the solution given. So as we have discussed, any vertex in a graph having n vertices can have maximum n minus 1 degree. So therefore, degree 4 is the maximum degree that this graph can have. So option C is incorrect. So so everyone understood this point, right?
Yes, sir.
Yeah. And now we'll find the sum of the degrees of all vertices. It must be even. Therefore, option B turns out to be 7, which is an odd number. Therefore, option B is incorrect. Okay. And in step 3, we are finding as I discussed, if two vertices in a graph have degree n minus 1, it means that there will be no vertex with degree 1. Okay. So vertices A and B have degree 4. Therefore, option A is also incorrect. Because option B, the vertex D and E have degree 1, I guess. So that option is also incorrect. So the only possible answer is option D. Okay. So can we move to the next topic now?
Yes, sir.
Yeah. So now, what is an adjacency matrix? We'll see. A matrix with rows and columns labeled with graph vertices, and all the entries in it are either 0 or 1. Entry ij is 1 if there is an edge from I to j. It is 0 if there is no edge from I to j. So yeah, we'll see an example. Suppose this is a graph G given. So what we'll do, we'll just write A, B, C, D, E here and A, B, C, D here. Okay, just a minute. Yeah. So this will be the adjacency matrix of G here. Okay. So see, A to A there is no edge, so it is 0. The diagonal elements, if you notice, it will be 0. Okay. So, but if you see A to B, there is an edge, right? Hello?
Yes, sir.
Yeah. Yeah, in A, B, we'll mark 1. Similarly, A to C, there is an edge, we'll mark 1 again. A to D, there is an edge, we'll again mark 1, and A to E also there is an edge, we'll again mark 1. Whenever there is an edge in this graph, we'll mark 1, else we'll mark 0. Okay, B to E, there is no edge, if you can see. Therefore, then it will be marked as 0. So this will be the adjacency matrix of this graph. So everyone understood this concept?
Yes, sir.
Yeah. So from this concept, we'll just see the maximum number of non-zero entries in the adjacency matrix of a simple graph having 5 vertices. So they're asking a graph has 5 vertices. So what can be the maximum number of non-zero entries? So how many number of ones can be there? Okay, that is what they're asking. What is the maximum number of one? Okay, you're getting it? You're getting the question?
Yes, sir.
Yeah. So I request everyone to solve this question. If you have any doubts, you can unmute and ask. So you guys want to see the previous slide?
Yes, sir. Actually, I want to understand like what does it mean by rows and column labeled with graph exactly?
Just a minute. See, so what we'll do is we'll just mark the vertices here, A, B, C, D, E, and A, B, C, D, E here. Okay. And if there is an edge from A to B, we'll mark it as 1. If there is no edge from A to B, we won't mark it. For example, if you can see from B to E, there is no edge here, right? So therefore, it will be marked as 0. You're getting
Yes,
it?
sir. Got it. Got it.
Yeah. So this question they're asking what can be the maximum value? I mean, how many ones can be there in the adjacency matrix? Maximum number of ones. Okay, where the number of vertices is 5. Okay. Yeah.
Sir, can we proceed with the question?
Can we discuss the answer now?
Yes,
Yes,
sir.
sir.
Okay. So they're asking the maximum number of non-zero entries in the adjacency matrix of a simple graph having 5 vertices. Okay. So what can be the answer?
Sir,
20.
20.
20, right? So someone got option A. So can you just unmute and explain like why you got option A?
Sir, because diagonal matrix is 0.
Yeah. So therefore it can't be 25, right? So
Yeah.
this is 5 vertices. So the adjacency matrix can have 5 cross 5 entries, but we know that the diagonal can be 0, right? Diagonal should be 0, right?
Yes,
Yes,
sir.
sir.
There will be at least 5 zeros. So there are 25 places possible, but 5 will be 0. Therefore 20 can be the maximum number of non-zero entries. So just a minute, we'll just see the solution again. Yeah, see. So consider 5 vertices A, B, C, D, and E. If we have an edge between every pair of vertices, then we'll have maximum non-zero entries in the adjacency matrix, right? If every edge is connected with all the other edges, then there will have maximum number of non-zero entries, right? Hello?
Yes, sir.
Yeah.
Yes, sir.
So this will be the graph. This is also called as a complete graph where every edge is connected with each other. Okay. So if we just try to draw see the adjacency matrix of this graph, we can see that it will be like this. The diagonal entries will be 0, but in every other places there will be 1. Okay, like there will be totally 25 entries here, but 5 of them should be 0. Therefore, the maximum non-zero entries would be 20. Okay, so yeah, we'll just see it. Yeah, the total number of entries is 5 into 5, 25. The number of non-zero entries, number of zeros entries would be 5, and the total number of non-zero entry would be total entries minus number of zero entries, which would be 20. So everyone got this question? Are there any doubts here?
No, sir.
Sir, formula for this one is n into n minus 1, right?
Sorry.
Sir, for this, if we have to calculate through the formula, it will be n into n minus 1.
Yeah, it is. Yeah, every edge is connected with all the other edges, right? So yeah, there are n edges,
So
and it
one
is
more thing, like here, the same thing was there in CT, but what we were doing there, we were doing n into n minus 1 by 2. But here, AB and BA is not differing. So, like, what is the logic behind that?
sorry.
So, like here, when there's a when there's an edge from A to B, and there is same edge from B to A as well.
It is an undirected graph, right? So if there is an edge from A to B, we'll just mark it as 1. Okay. So if there
Okay.
is an edge from A to B, we'll also mark it as there is an edge from B to A also. Okay.
Yeah, and that is the reason why in CT there was when there was directed. I don't exactly not getting, but it was n into n minus 1 by 2.
Maybe it might be for directed, I guess.
Yeah. Thank
Okay.
you, sir.
Sir, even in our in Max tutorial, also in one of the video, it was mentioned that for undirected it is n into n minus 1 by 2, and for directed it is mentioned as n into n minus 1.
Sorry.
Sir, for directed, it will be n into n minus 1, and for undirected, it will be n into n minus 1 by 2, because from A to B and B to A are same thing, right?
Okay. So they're asking about the non-zero entries here, right? So if you talk about in the context of adjacency matrix here, there are totally 20 non-zeros entry, right? So you're talking about the edge there. Okay.
Okay, sir.
Yeah, you're talking about the edge there,
Mm-hmm.
but
Okay.
here they're asking the number of non-zero entries. So how many ones will be there? Okay.
Yeah, okay, sir.
Yeah. So can we move to the next part here?
Yes.
So we'll now see about BFS tree here. So this is the graph, and we are doing a breadth first search starting from the node A. So everyone know how breadth first search work? Hello? Yeah. So first we'll start from node A, and we'll visit all other vertices which are connected with A. So which will be B and F here. And then like we can also move from the alphabetical order. We'll go to B and search all its neighbor. So it will be E, C. Again, we'll go to C. It will be D and G. So this will be the BFS tree, right? Yeah. So both the vertices at level I in BFS tree may be connected by an edge in the original undirected graph. See what they are saying. Suppose let's say this is level 0, level 1, level 2, and level 3. Okay. So if both the vertices at level I, if suppose two vertices are at same level, okay, they may be connected by an edge in the original graph also. Okay. So C and E are in the same level, right? So they may be connected in the original graph. See, but in this case, it is connected here. They may be. Okay, it is not always true, but they can be connected. We can see one more example, which is D and F is also connected. C, D, G. Okay. So, and the second point says that a vertex at level I and a vertex at level I plus 1 in the BFS tree may be connected by an edge in the original. Suppose let's take B and let's take C. B is at level I and C is at level I plus 1. Okay. So B and C can be connected. It is not saying it must be connected. It can be, it is saying that it may be connected. We can also see from the graph that they are connected. Okay. So it is not necessarily true. It can be true. Again, I'm just repeating that point. So the last point says that a vertex at level I and a vertex at level I plus 2 or higher. Okay, in the BFS tree will not be connected by an edge in the original undirected graph. So see, they are saying that if you take any vertex at level I and then go 2 levels or below that, they are saying there won't be any edge between those two. For example, if you see A, if you take A here, okay, and if you take C, E, D, G, okay, so you can surely say that there won't be an edge between A to E, A to C, A to D, or A to G in the original graph. So everyone got this point? Yeah. So just a minute. Yeah. So we'll just, there is nothing given about, yeah. This is the question actually. So suppose we obtain a following BFS tree rooted at a node A for an undirected graph. So this is a BFS tree. So the question asks which of the following cannot possibly be an edge in the original graph. Okay. So everyone got this question? Yeah. Yeah, I request everyone to solve this question. So this is kind of easy. So just use the concept that we learned in the previous slides. So I'll just sum it up once again. If two nodes are at the same level, they can be connected. There might be an edge. If two nodes are one level apart, so I and I plus one, then also there can be an edge. If two nodes are more than one level apart, so two or more, then there can't be an edge between those two nodes in the original graph. So they're asking which of the following there can't be an edge between two nodes in the original graph. Okay.
Sir, please discuss the solution.
Yeah. So can we discuss the solution? Everyone completed solving this question.
Yes, sir.
Okay. So we'll just see. So B to K, we can see that they are just one level apart, right? So there can be an edge. We can't say there can't be an edge. So option A might be. So option A is not the correct option. So we'll see M and N. So M and N also we can clearly see that they're just one level apart, right? So option B is also incorrect. We'll see E and I. See E and I, we can see that they are two levels apart, right?
Yes, sir.
Yeah. So option C, there can't be an edge between E and I in the original graph. So this option is correct. If you see from E to H, they are just one level apart, so there can be an edge. Okay. So option C is the correct answer. We'll just go to the solution now. So option A, B, C. B has level 2 and K has level 3 in this BFS tree. It is possible that they are connected. They can be connected. Okay. So they have also given an example graph of the same. So we'll see option B now. So M has level 4 and N has level 3. It is also possible that they can be connected. So there is again another example given here. This graph and the BFS3 of the same. So option B is not the correct option. So option C, E has level 3 and I has level 5. If E and I are connected, then I will have level 4 rather than level 5, right? So basically they are just two levels apart. So what we can say that there can't be an edge between E and I. Therefore, option C is correct. And option D can be explained like similar to option A. Like if we just take the same graph, we can see that there can be an edge between which one and which one? E and H. Okay. So can we go to the next part now?
Yes, sir.
Yeah. So vertex coloring of a graph. So find the minimum number of colors required to color all the vertices of the graph such that no two adjacent vertices have same color. So this has been thoroughly discussed in the lecture, right? So I'll just sum it up once again. So yeah, what we are first doing is fill the first color. So let us take any color red here, and we are starting from A. Okay. Since C and D are connected to A, we are not coloring with red. Okay. So now we are connected. Coloring E and G, because if F can't be colored with F color can't be red because it is connected with E as well and as well with C. So F can't have the color red here. So we'll just color the other vertices. H also can't have the color red. So we are coloring J as red, and K also can be colored as red, and Q also can be colored as red. Okay. So now we have exhausted the color now. So no other vertices can be colored with the color red, so that the adjacent vertices are not of the same color. So what we'll do, we'll just choose another color. Okay. So this time we are choosing the color green. So we are just trying to fill the gap. So we are coloring C with green and D with green. But F can't be colored with green because it is connected with D. Okay. Now we are coloring H here. So and we are coloring P. So B can't be colored with the color green because it is connected with H as well as it is connected with P. Okay. So now we have again exhausted the color both red and green. We'll move to the next color. So next color we can color both the F and B with the color yellow, right? So now we can see how many colors are required. 1, 2, and 3. Red, yellow, and green are the 3 colors that are required to color this graph such that the adjacent 2 vertices are not colored with the same color. So everyone got this concept?
Yes, sir.
Yes, sir.
So we'll come to the question. A company manufactures 10 chemicals. Certain pair of these chemicals are incompatible and would cause explosion if brought in contact with each other. So below graph shows the incompatibility of the chemicals. Each vertex represents the chemical, and each edge between a pair of chemicals represents that those two chemicals are incompatible. So as a precautionary measure, the company wishes to partition its warehouse into compartments and store incompatible chemicals in different compartments. So yeah, so that is the question. So we'll see the follow-up. I mean, this one. What is the least number of compartments into which warehouse should be partitioned? So there is also a hint given. Color the vertices in the graph so that no two adjacent vertices get the same color. Okay. So try to color this one and tell me how many colors are possible. I mean, what is the total number of colors required? Okay. We have to find the minimum number of colors required. So everyone got this question? Hello?
Yes, sir.
Yeah.
Yes, sir.
So to put the answer, suppose if 2 colors or 3 colors or 5 colors are required, just write 2, 3 or 5 in the chat box. Okay. So can we discuss the answer to this question?
Yes, sir.
Okay. So the correct answer would be 4. We'll see how. So first step, we'll just start with the vertex F here. So we can't color J and G with the color red because they are directly connected. And now we can color A again. So we can't color D, C, or E. Okay, with the color red. Now we'll color I here. So we can't color H with the same color. Okay, so if we choose one color for vertex F, then the color cannot be given to J, B, G as they are directly connected to F. So step 2 we'll see the color given to F can be given to A, but not to D, E, and C because they're directly connected with A. The last vertex, I can have the same color as F, but now H can't have the same color because it is directly connected with I. So now we'll choose the second color. Now we can choose second color for those vertices which are directly connected with the vertices having the first color. So we'll just use the color for the vertices which are directly connected with the vertices which are having color red. So we can choose G, J, C, and H also. But we'll see. Since we have given the color green to G, we can't color H here because it is direct. There is a direct edge between G and H. Now we can color J with the color green, and C also we can color it with green. But B, D, E, we can't color it with green again. So now we'll do D is also connected with A, but we cannot give it the second color as it is also connected with G. So the next step what we'll do is, just a minute. Yeah. So next step D can be colored with the third color, and similarly H and B also. Okay. So D, H, and B will color it with the third color. B is connected with C, therefore it is colored with it has the color blue, and G is connected with D, it has the color blue. And D is connected with H, which has the color blue. But E can't have the color blue because it is directly connected with D. Okay, so E should have a separate color. So from this graph, you can clearly see that there are totally 4 colors required to color this graph, so that no two graphs have same color. Okay. So everyone got this point?
Yes, sir.
Yes, sir. Yes,
Can
sir.
we move to the next one now?
Yeah.
Yes, sir.
So one more follow-up question is here. So we saw the a color graph in our previous slide. Now the question is, can we still add some more edge in the graph so that the coloring of the graph does not change? So they are saying, can there be any more edges that can be added to the graph so that the color remains same? Is it possible? Can someone tell me?
Yeah, it's possible.
Yes,
Yes,
sir.
Yeah.
G and P.
G and D is already connected, right?
G and P.
E, F, E and F.
Yeah. G and P, yes. G and P is correct. And A and
Sir, E and D.
yeah, E and D, right?
Yes,
Yeah,
sir.
E can be connected. Yes.
A and F.
H
There
and
are,
F also.
yeah, H and F, yeah. So the question answer. So basically, we can have we can add more edges so that the color of the graph remains same. Okay. So that's what we can see. Even F can be connected with A, C, and H also. Okay. See the first pentagon where A can be connected with E and F, but E has the same color as A, so we cannot connect A and E here. Yeah. So F can also be connected with C. In the rectangle, F could be connected with H also. Okay. So yeah. So they are saying that there can be more edge without altering the color sequence. Okay. So now we'll come to the planar graph. Planar graph means can we add see. So they are saying can we add some more edges to the graph so that the graph is still planar. So planar graph basically means we can draw the graph without intersecting the edges. Okay. So is it possible? They're asking. Can we add more edges so that this graph is still planar?
Yeah,
Yes, sir, we can.
Yes, sir.
two more we can
From
have.
C to D and C to F also we can draw, right? And also like it need not be like inner edge. Okay. So the edge can go outside also. You're getting it? Even this CD is an edge and D is also an edge. Okay. So first, what we'll see what they're doing. So if we start from the node A, we can see that we can connect E and F, right? A to E we can draw an edge, and A to F also we can draw an edge. So now C D can also be connected, but it will make the graph non-planar, because if we connect it this way, CD and CE, I mean not CE, CF, so then the graph will be non-planar. So what we are doing, we are just therefore we connect C and D via an outer edge. So we are just taking the edge outside and then connecting it. Like in the previous case, we can also connect D and E. Okay. So yeah.
So maximum 4 is possible in this.
Sorry.
Maximum 4 edges can be added in this.
Yeah. We can see that like maximum 4
Sir,
edges.
can't it be E to A?
See, E to A, if you start, E to A is already there, right? A to E is there, so E to A is also there. This is undirected graph, right?
Okay. Yeah, okay.
Yeah. We move to the question now. An incomplete undirected graph is shown here, and the numbering of each vertices denote the coloring of the graph. So if it is one, let's say, like let us assume they are of the same color. Okay. So 1 denotes to color 1, and 2 denotes to color 2, and 3 denotes to color 3. Find the maximum number of edges that can be added to the given graph such that the coloring is retained and the graph is planar. Okay, so basically you can't connect 1 and 1 here because the coloring color is same, therefore we can't connect. Okay, and the edge also can't intersect. So just try to draw that and tell me what are try to maximize the number of edges that can be drawn, and tell me how many number of edges can be drawn so that these two properties are displayed. The graph is planar as well as the coloring is retained. Okay, so everyone got this question?
Yes, sir.
Okay. So even in the hint is given, try to maximize the number of inner edge and then draw the outer edge. Okay, so these things, like if you connect 1 to 2 like this, those are inner edges, so try to maximize that first and then draw the outer edges. try to connect like maximum number of edges. Like for example, this 2 can be connected to this 3 also via an outer edge. So if you draw like this, it will be connected like here. So like try to maximize the number of edges that can be drawn. Okay. Can we discuss the answer in 2 more minutes?
Yes.
Many got 7 here. Okay. So there can be more than 7. So try to maximize it. Okay, like you can also tell how much inner edge you got, total number of inner edges that you got. Just type inner edge and then type the number. For example, type inner edge is equal to like 4, 5, 6 or something, and then type outer edge is equal to 3, 4, 5 or something. Okay, I got one answer. Yeah, there are 4 possible inner edges. That is correct. But outer edge, just try to draw more outer edges. If you guys are telling the inner edge is 4, just kindly type 4 inner edges. Okay. Yeah. I'll just give 2 more minutes. Yeah, 4 inner edges correct, but many are not getting the outer edges correct here. So try to work on that again. Only one got the correct answer. No, outer edge also can't intersect. No edges can intersect. Okay.
If we consider the three colors as a matrix, 3 by 3, can you find the answers?
No, no, like you can just try to draw the edges directly from the graph. Yeah, now someone getting the correct answer. You can just directly draw it, like, but make sure that those two properties are there. You can't put an edge between the same color vertices, and the edges also can't intersect. Even outer edge can't intersect. So can we discuss the solution for this question?
Yes, sir.
Okay. Yeah. So the correct answer is 9. There are 4 inner edges and 5 outer edges. We'll see how. So, yeah. See, we can see that there can be only 2 inner edges here, right? So it's from 3 to 2. The maximum number, there can be 0 also, but we are trying to maximize it. So here in this one, in this figure, like you can see here are 2 from here and 2 from here, right? So there are 4 number of inner edges. Many got that correct. So now we'll see the outer edge. See, there can be an outer edge from 1 to 2 and 1 to 3 as well, right? And there can be an outer edge from 2 to 3, 2 to 1, and 2 to this 3 also. So totally there are 5 outer edges and 4 inner edges. So therefore, the maximum number is 9. Okay, you can't have any more edges, so that those two properties are still satisfied. So everyone got this?
Yes, sir.
Yeah. So the correct answer would be 9. So can we move to the next topic now?
Yes.
Okay.
Yes, sure.
Next topic. So we are going to see what is DAGs, some facts about DAGs. DAG is directly acyclic graph. So they do not have any cycles. Okay. So cycle, 3 vertices which are, which form a loop. We don't say 2 vertices which are connected with each other. We don't say it as a cycle. If 3 or more vertices are connected and they form a loop, we call it as a cycle. So directly acyclic graph does not have any cycles, and every DAG has a vertex with in degree 0. And in degree means the number of edges which are coming towards it. Okay. So, and you know that this is also directed, right? So since they're directed acyclic graph, this is not undirected, this is a directed graph. So every DAG has in degree 0, and every DAG has a vertex with out degree 0. So there should be a vertex with in degree 0, and there should be a vertex without degree 0 in DAG. Okay, and topological sorting and longest path can be solved on DAG. So we'll just see. So what is topological sorting first? We'll write all the in degrees, write the in degrees of all the vertices of DAG. Suppose let's say the in degrees are 1, 3, 5, 4 respectively. So we'll just take something and find a vertex u from the DAG which has in degree 0. So one must have 0. So we'll just take the in degree 0. I mean, just choose the vertex such that it's in degree 0. Okay, and we'll add the vertex to the topological sequence. We'll just add it to a sequence now, and we'll remove the vertex from the DAG. Suppose, okay, we'll remove the vertex from the DAG and update the in degrees of each of the remaining vertices. So we'll just repeat the process until we form the topological sequence. I'll just give an example. You guys need an example or something?
Okay.
Okay, so we'll just go to the question. So Suresh needs to perform it. Okay, so I think this is a question. Yeah. So everyone can see this question, right?
Yes, sir.
Yeah. So Suresh needs to perform 6 tasks, namely P, Q, R, S, T, U. Some tasks need to be performed after performing a particular task. The below table shows column 1 shows the task and column 2 shows the set of tasks that can be performed only after performing the particular task. Okay, so this is what they're saying. Suppose, so everyone understood this question, right?
Yes, sir.
So column 2 is the
This is
dependency.
yeah.
That means for before P, Q and R should complete.
Column is no, only after completing P we
P,
can
Q, and R.
no
Q
only
and
after
R. Okay.
completing P we can complete Q and R.
Okay. Good.
Okay. So this is column 2. It says that column 2 shows a set of tasks that can be performed only after performing the particular task. The particular task is here. Okay. So we'll have to see which has in degree 0. Just try to plot the number of in degrees here and then pick the one which has in degree 0 and follow the steps. You will find the topological sequence. And yeah, you can enter the answer in the chat box, enter the letters in order separated by comma. And one more thing, there can be more than one option correct. I mean, you can get two sequence. For example, A, B, C, D, E can be one thing, or A, B, C, E, D also can be the other one. Okay. I'm just giving an example. So the sequence can differ, but if you get the sequence, just type the letters and post it in the chat box. Okay.
Sir, please discuss.
Okay, so can we discuss the answer to this question?
Yes, sir.
Okay, so we'll see. We represent the given data as a graph G with in which each task represents a vertex and each directed edge from I to J if I needs to be done before J. So for example, A and B are two tasks and task B can be performed only after task A. So we'll write a directed edge from A to B. Okay. So now it is enough to find the topological sequence of vertices to get the order in which Suresh has to perform the task. So we'll just try to use this list and draw the graph now. So yeah, draw the graph of G using the given table. So the graph will be like this. See, you can see that T to U there is an edge and T to S there is an edge. Similarly, like if you can see S to P there is an edge and S to R there is an edge, and from R to Q there is an edge, and P to R. So we are just basically drawing the edge which are given in the list. Okay. So can someone tell me which has in degree 0 here?
T.
T, right? So any
Yes,
other nodes have in degree 0?
No.
No, sir.
No, right? So we'll just observe that the given graph is DAG. So there is at least one vertex which has good, and there is also no vertex which has there is no out degree for Q also, if we can see, and there is no cycle here. So it is following all the properties of DAG, right? So yeah, the obtained graph is a DAG. So find the integrity of all the vertices of the graph. So we can see that 0, 1, 2, 2, 2, and 1. These are the integers here. And find the topological sequence now. So vertex T has integrity 0 now. So we'll choose that. Remove the vertex T from the graph. Basically, we'll just remove this and its corresponding edges also. And we'll add it to the topological sequence. So now if we remove T, what will happen to the integrity of U and S? Hello? Am I audible?
0, sir.
Yeah.
Yes, sir.
0, sir.
So this edge will be removed and this edge will also be removed. So both of them will have again 0 integrity, right? So yeah. So first the topological sequence we'll just add T now. So update the remaining integrity of each. Update the integrity of each remaining vertices in the graph. So U will be 0 and S will be 0. The others will remain same. Now we have to again choose a vertex with integrity 0. We can either choose U or S also. Correct? So remove any one of them. It's your choice. You can either choose U or S. It's up to you. Suppose in this case we are removing U here. Okay. So U is removed. So first we'll add it to the sequence now. So the topological sequence will be T comma U. Okay. And now we have to remove that U and remove the corresponding edge also. And we have to update the integers. So which integer will change? Which of the vertex there will be a change in the integrity?
P.
P, right? So what will be the new integrity of P?
1,
0.
1.
1.
This is not removed, right? There is still an edge from S to P, right? S is not removed.
Okay.
Correct?
Yes, sir.
So it will be 1 here. So now we can see that the integrity of P is 1, S is 0, R is 2, and Q is 2. Now we have to remove again S only because there is no other choice. So we'll remove S and add it to the topological sequence. So it will be TUS. Okay. Now we'll again remove the corresponding edges to S. So P and R, there will be a change in integrity. So yeah, update the integrity of each of the remaining vertex in the graph. So now if we remove this edge and the corresponding edges, we'll get this graph, right? So there will be a change of integrity to P, R. Okay, so it will go from 1 to 0 and this will go from 2 to 1. So we can observe it here. Now again we have to remove the vertex P because it has integrity 0 and we'll add it to the topological sequence. So the sequence would be T, U, S and P now. So yeah, we'll just follow the same procedure. If we do that, so R will have now integrity 0 and Q will have integrity 1. So we can see that now we'll remove R and add it to the topological sequence, and then finally we'll add Q. Okay. So this is one of the possible topological sequence here. So we can say that he should perform the task in the order TUS, P, R, and Q. See, but as I said, this can't be unique, right? Because in that case, like I think in that case we could have chosen S instead of U, right? So there were two vertex with degree 0. So we could have chosen any one of them. So we chose U in that case. If we choose S instead of U, so this would be the topological sequence. Okay. So one point that we can note here is topological sequence is not unique for a given DAG. Okay. So everyone got this point? Are there any doubts in this question now?
It's after the T, as why we have taken no, in the first one, the TU, after that S we are taking instead of P.
Which one?
Yeah, yes. Here, after U, we are removed the P, but we are taking S as the topology.
See, we are removing U here, right? So
Yes.
P will have in degree 1 now, right? And S will have in degree 0. We have to choose. So this will be the graph. If we remove U now, this will be the graph.
Yes,
And the
sir.
updated in degree. So we can only choose S, right? We can't choose P, correct?
Okay, from 0 to 1.
Yeah. Okay.
Yes.
So that's why we have to add S only. And yeah. So any other doubts? So these two are the possible answers. Okay. So yeah, this is the end of this session. Yeah, before leaving this session, I request everyone to fill the G form given in the chat box. If you have any doubts in this session, you can ask. So are there any question which you couldn't find the answer? Or did you face any difficulty? You can ask it now. If not, like before leaving this meet, kindly fill that form and leave the meet. Okay.
Yes, sir.
Okay.
Thank you.
Okay. Thank you.
Thank you, sir.
Yeah. Thank you.